In late 2024, a surge of online chatter ignited around a chilling rumor that Google's quantum computer created an image of the observer, and what appeared was chilling. The story, vague yet compelling, spread rapidly, capturing imaginations with eerie implications of consciousness emerging from code. But behind the viral mystique lies a far more grounded and remarkable reality. Today, we'll unearth the full truth. Google's quantum computing efforts. Google's foray into quantum computing began in earnest in 2013 with the establishment of its Quantum AI Lab, a collaboration initially involving NASA's Ames Research Center and the University Space Research Association. Located at Google's research hub in Santa Barbara, California, the lab was created to investigate the frontiers of quantum information science, with a long-term vision of developing practical quantum processors. At the time, Google's approach stood apart from traditional computing projects. The lab focused specifically on superconducting qubits, which are circuits cooled to near absolute zero and manipulated using microwave pulses. These early efforts paved the way for what would become one of the most aggressive and well-funded quantum computing programs in the world. In October 2019, Google publicly claimed to have achieved quantum supremacy. The term was coined by theoretical physicist John Preskill to describe the point at which a quantum computer can perform a task beyond the capabilities of classical supercomputers. This claim was based on the performance of Google's Sycamore processor, a 53-qubit superconducting chip designed and built by the Quantum AI team. In a Nature paper published on October 23, 2019, Google researchers reported that Sycamore completed a specific random number sampling task in 200 seconds, something they estimated would take the most advanced classical supercomputers approximately 10,000 years to complete. While the task itself had no direct practical application, it served as a powerful benchmark to demonstrate quantum computational advantage. It also marked the beginning of serious, results-driven quantum engineering at scale, providing researchers with a platform to study entanglement, decoherence, and quantum error modeling in real hardware. However, Sycamore's performance also highlighted the field's limitations. The system was not fault-tolerant, meaning that its qubits were too noisy and error-prone to support large-scale quantum algorithms. To move beyond quantum supremacy toward useful quantum computation, Google recognized the need to solve the fundamental challenge of quantum error correction, a requirement for building reliable logical qubits that can survive the natural instability of quantum states. This understanding culminated in the next major breakthrough, the announcement of Google's Willow processor on December 9, 2024. Housed once again at the Santa Barbara campus, Willow is a 105-qubit superconducting chip designed to test quantum error correction protocols at scale. Its core achievement lies in being the first quantum system to surpass the so-called error correction threshold. This threshold, proposed by mathematician Peter Shea in 1995, defines a tipping point in fault-tolerant quantum computing. If individual physical qubits can be arranged in such a way that the overall logical error rate drops as more qubits are added, then scalable, error-corrected quantum computation becomes theoretically possible. Willow successfully demonstrated this principle using a surface code architecture, a two-dimensional lattice of physical qubits that encode one logical qubit. In a reported experiment, researchers grouped Willow's qubits into patches and incrementally increased their size while monitoring the logical error rates. As predicted by Shea's model, they observed that the logical error rate decreased exponentially as the number of physical qubits grew. This was the first time this happened in the history of quantum computing. Prior systems had required additional qubits just to maintain the same error rate. Willow reversed that trend, proving that the road to practical quantum error correction was no longer just theoretical. In terms of technical performance, Willow featured substantial improvements in qubit coherence times, reaching nearly 100 microseconds, and enhanced gate fidelities that allowed for more complex operations without sacrificing accuracy. The team achieved these gains through refined fabrication processes, better cryogenic engineering, and improved microwave control systems. These advances were critical not just for the error correction experiments, but also for benchmarking tasks. Willow completed an updated random circuit sampling task in under 5 minutes, a feat that, according to Google, would take the most advanced classical supercomputers more than 10 quadrilogitillion years. With 75 zeros, a number so vast it dwarfs the age of the universe by orders of magnitude. Let's dive deeper into the specifics of the system's capabilities, performance, and benchmarks. The random circuit sampling task in question involved Willow executing a series of controlled quantum operations or quantum gates on a 105-qubit array. The resulting probability distribution was so complex that classical simulations attempting to reproduce the same outcomes would run into computational bottlenecks almost immediately. This benchmark, similar to the one used in 2019 by Sycamore, which performed a 200-second task estimated to take classical systems 10,000 years, is not designed to be practically useful in a commercial sense. Instead, it functions as a stress test, pushing the quantum processor to perform at full capacity and allowing researchers to evaluate its operational speed, coherence, and fidelity under demanding conditions. Despite the jaw-dropping numbers involved, random circuit sampling does not currently translate into real-world applications. Tasks such as breaking cryptographic codes, modeling molecular interactions, or optimizing complex systems still remain out of reach for quantum processors like Willow. Random circuit sampling is, by design, an artificial benchmark. It demonstrates quantum computational advantage but does not directly solve problems relevant to industries or scientific research. Critics of the benchmark often point out that while it proves a theoretical edge, the lack of practical utility tempers its broader significance. However, defenders argue that such benchmarks are critical stepping stones, providing the only current method to measure tangible progress in the still-developing field of quantum computing. What makes Willow's achievement more than just a repeat of Sycamore's milestone is a hardware sophistication that enabled such performance. Central to Willow's design are significant technological innovations aimed at making quantum computing more reliable and scalable. One of the key improvements was in coherence time, which is a length of time a qubit can maintain its quantum state before decohering due to noise or interaction with the environment. Willow pushed this metric to approximately 100 microseconds, a notable improvement over earlier processors like Sycamore, whose coherence times average around 20 to 30 microseconds. Longer coherence times allow for more operations to be performed before the system collapses, enabling deeper circuits and more complex calculations to be run without losing accuracy. Equally vital were the improvements in gate fidelity and readout reliability. Gate fidelity refers to how accurately quantum gates, which are the basic building blocks of quantum algorithms, can manipulate qubits. High-fidelity gates are essential for quantum error correction, as even small inaccuracies can compound across large systems and derail computations. Willow demonstrated gate fidelities exceeding 99.9% for single-qubit operations and nearing similar thresholds for two-qubit gates, an achievement made possible through more precise microwave control electronics and reduced crosstalk between neighboring qubits. Readout fidelity, which concerns how accurately the final state of qubits can be measured, was also optimized to reduce false readings and data loss during computation. The layout architecture of Willow represented another major advance in the direction of scalable quantum computing. Willow employed a modular chip design, allowing researchers to partition the 105 physical qubits into functional patches that could be used for logical qubit encoding through surface code protocols. This layout not only supports better error correction but also facilitates the construction of larger processors in the future by interlinking multiple modules. Interpretive frameworks and public reactions. Many believe that quantum computers may, in some abstract sense, be drawing upon multiple realities to perform calculations. This notion has often been associated with the many-worlds interpretation of quantum mechanics, a framework first proposed by physicist Hugh Everett III in 1957. According to this interpretation, every quantum event results in the branching of the universe into parallel outcomes, effectively creating a multiverse where every possible quantum state exists in some version of reality. Though this view is highly speculative and remains one of several competing interpretations, it has gained a foothold in both academic circles and public discourse, particularly as quantum computing advances have prompted deeper inquiries into how such machines actually function. A notable voice in this conversation has been Dr. Hartmut Neven, founder of Google's Quantum AI Lab, and a key figure in the development of both the Sycamore and Willow quantum processors. In several interviews and public talks, Neven has referenced the many-worlds interpretation as a metaphorical framework for understanding quantum computation, particularly when discussing quantum speedup. He famously remarked in 2019 that quantum computing power seemed to be growing doubly exponential, and joked that Google's quantum computer might be sampling results from parallel universes. However, the many-worlds interpretation, while intellectually stimulating, remains purely theoretical and does not imply that quantum computers actually access alternate realities. The field of quantum computation operates under well-understood principles of quantum mechanics, such as superposition and entanglement, which are mathematically rigorous and experimentally verified. The advantage of a quantum processor stems from its ability to encode and process information in qubits that exist in superposed states, allowing for parallelism in computations that classical bits cannot achieve. The actual mechanism by which quantum computers solve problems involves unitary evolution, error correction, and measurement, all of which are grounded in empirical physics. Despite this, the allure of the many worlds interpretation has had a noticeable impact on public perception. In the wake of Google's announcement of the Sycamore processor's quantum supremacy in October 2019 and again with the launch of the Willow processor in December 2024, social media platforms, online forums like Reddit and Hacker News, and even some popular science outlets saw a flood of speculation. Many commenters referenced the possibility that quantum processors were communicating with other universes or awakening something conscious, often blending legitimate scientific terms with imaginative but inaccurate extrapolations. The situation intensified in late 2024 with the emergence of viral posts claiming that Google's Willow processor had produced a human-like observer figure during quantum computation. The rumor gained traction across TikTok, YouTube, and fringe tech blogs, often accompanied by altered images and speculative commentary invoking the many worlds interpretation or other metaphysical theories. Let's now unveil the reality of the observer. The observer image myth. Social media was abuzz with the claim that Willow had generated a mysterious image of an observer, a human-like or humanoid figure that appeared during a quantum computation process. The story was quickly amplified by influencers on platforms like TikTok, YouTube, and X, formerly Twitter, who presented grainy visuals and loosely connected them to quantum theory and metaphysics. Some claimed the image had emerged from quantum noise, while others asserted that the observer was evidence of quantum computers interacting with parallel dimensions or consciousness fields. However, despite its viral appeal, this entire story is demonstrably false. There is no scientific evidence or official documentation to support the claim that Google's Willow processor ever produced any such image. No peer-reviewed research paper from Google's quantum AI team, and no technical report from affiliated institutions, including the University of California, Santa Barbara, where the hardware was developed, has mentioned or acknowledged any such incident. Furthermore, no reputable media outlets such as Nature, Science, MIT Technology Review, or Wired has reported anything remotely similar. Google's December 9, 2024, technical blog post, which accompanied the release of Willow's breakthrough results, focused exclusively on quantum error correction, qubit architecture, and benchmark metrics. The content included no references to visual outputs or anomalous phenomena. Google's quantum AI lab operates under strict scientific protocols, and its breakthroughs are published only after internal validation and peer review. The Willow announcement followed this model, detailing a significant leap in achieving below-threshold quantum error correction, a cornerstone requirement for scalable quantum computing. Any extraordinary or unexpected result, such as a mysterious image emerging from quantum computations, would have been rigorously investigated, documented, and scrutinized before being shared publicly. The absence of even a hint of such a phenomenon in any verified publication strongly indicates that the observer's story is a fabrication, likely driven by internet folklore. Several viral posts use the term observer in a philosophical or quantum theoretical context, referring to the measurement problem in quantum mechanics, where the act of observation collapses a quantum state. However, this technical concept was quickly reimagined into something visual and literal by speculative storytellers. Some posts even used AI image generators to create eerie, stylized humanoid figures labeled as quantum outputs without disclosing that these were fictional composites, not real scientific data. The result was a viral campaign built entirely on conjecture, digital manipulation, and pseudo-scientific language. In reality, Willow's work does not involve any visual image generation at all. Quantum computers like Willow operate on qubits or quantum bits that exist in superposition and interact through entanglement. The output of a quantum computation is typically a probabilistic string of binary results of zeros and ones, which researchers analyze using classical statistical techniques. There is no graphical interface or visualization layer that would spontaneously generate human-like images during computation. The only visualizations involved in quantum computing are circuit diagrams, data histograms, and error rate graphs. None of these resemble or imply sentient forms or mysterious figures. Moreover, the Willow is a noisy intermediate-scale quantum device. This term, coined by John Preskill, refers to quantum processors with between 50 and a few hundred qubits that are not yet fault-tolerant and are still limited by high error rates and decoherence. Willow's key innovation was its ability to demonstrate below-threshold quantum error correction using surface code, a method that showed logical error rate decreasing as the number of physical qubits increased. This is a vital step toward building scalable quantum systems, but does not yet enable useful, large-scale computations. Looking ahead, the path to functional, fault-tolerant quantum computers will require several major engineering breakthroughs. First, researchers need to scale physical qubit counts from the current range of 100 to 200 to the millions, which will allow for the construction of stable logical qubits capable of executing long, complex algorithms. Second, gate and readout error rates must be pushed down to levels below 0.1% or better across the board, which will involve innovations in materials science, cryogenic engineering, and microwave control systems. Third, the development of real-world quantum algorithms for chemistry, cryptography, machine learning, and optimization will need to accelerate in parallel to ensure that once fault-tolerant systems arrive, they have meaningful tasks to perform. Google's roadmap for achieving this future is ambitious. The company has stated its intention to build a system with thousands of logical qubits by the early 2030s, which would require tens of millions of physical qubits operating under tight error margins. To get there, Google plans to incrementally scale hardware, refine modular architectures, and deepen its collaborations with academic institutions. The Quantum AI Lab continues to publish open-access results and collaborate with global researchers to standardize benchmarks and explore scalable quantum architectures. Nowhere in this roadmap, however, is there any mention of a requirement for mysterious images, sentient observers, or metaphysical manifestations. But there's a lot more to get you truly excited. Key discoveries that should excite you. Quantum computing is not science fiction anymore. Over the past decade, engineers and physicists have achieved milestones that mark the transition from experimental curiosity to a potentially civilization-shaping technology. While today's quantum computers are still in their infancy, the breakthroughs made in just the past few years represent leaps in both scale and capability. One of the most talked-about moments came in October 2019, when Google's Quantum AI Lab announced that its Sycamore processor had achieved quantum supremacy. This meant the quantum processor solved a specific mathematical problem in about 200 seconds, a task that would take the world's fastest supercomputer 10,000 years. Fast forward to December 2024, and Google's next-generation Willow processor demonstrated below-threshold quantum error correction. This is enormous. Quantum computers are notoriously fragile. Error correction is essential for any practical quantum computer, and below-threshold means that as more physical qubits are added, the logical error rate actually goes down. This milestone is necessary for scaling up to thousands or millions of qubits that will be needed to perform useful computations in physics, chemistry, and optimization. Scalable, error-corrected quantum computers promise to transform industries by tackling problems classical machines struggle to solve. In pharmaceuticals, they could revolutionize drug discovery by accurately simulating molecular behavior and protein folding, cutting development timelines from years to weeks. Companies like Quantum Motion, Zapata, and D-Wave are already testing such simulations with pharma giants. In materials science, quantum computing could unlock breakthroughs in superconductivity, battery chemistry, and solar energy, with Volkswagen, for example, using quantum simulations to improve lithium-ion battery design. Catalyst modeled that the quantum level might even enable low-carbon manufacturing processes. Optimization is another game-changer. Quantum algorithms like quantum approximate optimization can solve complex logistical problems more efficiently than classical methods, with Airbus and BMW leveraging them to streamline routing and production planning. In cryptography, the quantum threat is real. Algorithms like Shears could eventually break widely used encryption systems, prompting the urgent development of post-quantum cryptographic standards now being adopted by governments and financial institutions. Quantum computing is also poised to reshape artificial intelligence. Techniques like quantum kernel estimation and variational quantum classifiers may outperform classical deep learning in specific contexts, especially with noisy or high-dimensional data. Toolkits from IBM and Google, such as Qiskit and Cirq, already support hybrid quantum classical workflows, often via cloud access. What makes this all so exciting is not just speed. It's a fundamentally new form of computation. Quantum systems operate in multidimensional spaces, allowing us to model and manipulate reality in ways previously impossible. They are not just faster calculators. They represent a new scientific language. Though engineering hurdles remain, the progress is undeniable. In the coming decades, quantum computers are expected to evolve from specialized devices into foundational engines driving research, industry, and technological transformation worldwide. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.